Alright, we're now going to talk about a new topic, which is topic 2, work, power, energy. Okay, so naturally there are three aspects to this topic: work, power, and energy. Alright, so work is basically the work done to something okay. The formula for work is a certain force multiplied by a distance. Okay, so imagine you are pushing a block, okay, using the F over a distance, okay, D. Okay, so push from here to here, right? Okay, so the work done by you by this force would be force times distance. Okay, and the unit is in joules. Okay, J for joules. The same thing can also be said if you are applying a torque. Okay, for example, if you have a lever, okay, you are pushing the lever, applying a torque, okay, over a certain distance. But what distance are we talking about here? Okay, this center is definitely not moving, right? But the lever is moving. Okay, so the lever is moving over an angle of theta. All right, so for this case, the work done for this example would be a torque multiplied by the angular distance theta. Okay, note that the unit is Newton meter for torque, and theta will be radians. Okay, and both multiplying them will still give you joules as a unit. All right, power is the rate at which the work is being done. Okay, the rate means, okay, meaning the work done over time. Okay, the amount of work that you have done over time. Okay, which is force times distance over time. If you look at this formula, distance over time will actually give you speed, right? Velocity. So it's also force times velocity. Okay, and if you are looking at the rotational work, it would be, okay, torque times, power would be torque times, instead of linear velocity, it will be angular velocity, omega. Okay, so this is radians per second. Okay, this velocity would be meter per second. All right. Okay, the last part is energy. Energy, there are a few things to look at. Okay, energy. Okay, there are a few kinds of energy lah. Okay, the first two we know very well is your kinetic energy, KE, which is split into two. Okay, the first one is your translational kinetic energy, meaning linear motion. Okay, like a car going from one place to the other. Okay, and then the other one is rotational, meaning the rotation of the wheels, okay, also has its own rotational energy. Okay, so for this case, our translational is what we commonly remember as half mv squared. Okay, but rotational have a similar format, but instead of m you use I. Okay, instead of v you use omega. Okay, so it's I omega squared. Okay, both will also give you joules. The unit for energy is still joules. All right, so total kinetic energy is usually, total KE will usually be translational plus rotational. Okay, and for a wheel, for example, a wheel moving at a certain velocity v, right? Okay, how do you look at the rotation? If you position yourself at the center of the wheel, you are no longer looking at, you no longer see the velocity, but you actually see the rotation if you are looking from the center of the wheel, right? So what kind of rotation is this? It would be, if the wheel has a radius r, right? Okay, v over r. Okay, that's how you get the rotational speed of the wheel, v over r. Later you will see how it is being applied. Oh. Okay, the next one is your potential energy. Okay, this one we also are very familiar, which is mgh. Okay, mass times gravity times the height. Okay, the key here is that the h can be defined by you, by yourself. Okay, let's take an example. If you put, if you have a table, right, and you hang the object at a certain distance away from the table, h1, okay, you can say that the potential energy is mgh1 with respect to the table. Okay, but if you look at the ground, okay, the height is a totally different thing, right? h2. So now the PE is mgh2, but this PE will be with respect to the ground. Okay, so the key is always define with respect to what. Okay, what's the impact of this? If I define the ground as with respect to the ground, right, it means that the ground, anything that is at the ground has a zero potential energy. Okay, so if I define the ground as zero potential energy, the object will have a potential energy of mgh2. Okay, if I define the table as zero potential energy, the object will have potential energy of mgh1. Okay, so the reference level, the reference line is very important. Okay, and we will apply it in the actual questions later. All right, and then we have spring. Okay, spring energy. We're still on energy. Okay, so you have two kinds of spring. Linear spring, okay, the one which we usually see. Let's say this is undeformed, unextended length, right? And sometimes it get extended by this much, x. Okay, then the potential energy for this case okay, the spring energy for this case will be half kx squared. Okay, how much it extends. All right. Sometimes there are compression springs. Okay, so how much they get compressed. Okay. So it's the same concept. So your spring energy for a compressed spring will be half kx squared as well. Okay. This is a linear spring. Okay. The other kind is where you instead of pulling, you turn it. Okay. Example is something like this kind of spring. Okay. It undeformed, it has this shape, but you can actually pull it to make it wider, right? To make it wider. Okay. So how much do you pull it? You pull it by this much, theta. Okay. The angle now is the angle of extension. Okay. So this kind of spring will also have spring energy, which will be half k theta squared. Okay. Likewise, if you compress it the other way, it's also the same lah. Okay, it has a certain spring energy. Okay, so all these k's are the stiffness. Okay, the stiffness of the spring. The higher the stiffness, the more energy it will have. But it also means that the more force you need to pull it, because if I want to pull this by x, the spring force required will be kx. Okay, if I want to turn this spring by theta, the spring force required, right, will be k theta. Okay, so take note of that. And we have a diagram, a spring force extension diagram, and the relationship is actually linear. The higher the extension, the more force you require, and the gradient is actually your k. Okay, gradient is K. Okay, and if I want to stretch out this much, right? Okay, I need this force, right? In fact, the energy is your area underneath this force extension curve. Okay, so just to let you know, this is your energy, and this is your this is also your work done. Okay, in order to stretch. Okay, spring energy.